Okay, we're going to do the best we can to try and work out a couple projectile motion problems. We're going to start by looking at number 8 on the first page that we got the other day. World's largest flower pot is 1.95 meters high. So if you were to jump horizontally from the top edge of this flower pot at a speed of 3 meters per second, what would your landing velocity be? I'm going to start by drawing myself a little picture. So here's flower pot. Okay. Here's me, ready to jump off the flower pot, and my starting speed is going to be 3 meters per second along my horizontal axis right there. So I know from this right here that my delta y is going to be 1.95 meters. And they're wanting to know what's my final velocity. My final velocity is going to be a combination of this x velocity right here, as well as whatever y velocity I've picked up from falling. So I'm going to go ahead and I'm going to make myself a little a little cheater triangle down here. So this right here is going to be my final v that I'm looking for. I know that the x part of this v is going to be this 3 meters per second going that way. I don't yet know this is going to be my final velocity for y. And then I'll just do a little bit of clever Pythagorizing to figure out what final v is. Now we could go even further and we could figure out what angle I'm going to hit at. We may or may not do that. It just depends on how we're feeling when we get there. So we've got our picture, we've got our situation defined. We're going to make our XY table, like we usually do. So as far as what's on my X, I do not know, bless you again. I do not know my delta X. I do know my velocity of X, which is 3. For my Y, I know VO is 0. I don't know VF. I know my acceleration is 9.8. And I also, for both sides, do not yet know what my time is equal to. Do I know delta Y? I do know delta Y. Thank you very much. Yes. Very good. Let me do down then. Delta Y is 1.95. Yes, thank you. So, which set of information am I going to be able to use to get my time? The Y side. I've got a lot more info going on there. So when I look at my Big 5 chart, I want to find VF, but I also want to find T. So, Big 5 number 3, find T. I like it, because we don't need to know VF for that one. Okay, so doing our rewrite, should I go ahead and show all the parts of the rewrite thing? I do have it up on the board right there. I'm going to go ahead and just show it here in case anybody's watching this video and they're like, how the heck did you get there? If Big 5 number 3 is delta Y equals VO T plus 1/2 AT squared. Since VO is 0, we don't have to worry about that part. And if we want to isolate T by itself, we're going to multiply both sides by 2, divide both sides by A, and take the square root of both sides, so that T is going to end up equal to the square root of 2 delta Y over A. So, knowing that, let's do T squared 2 delta Y over A, which means that T is going to equal 2 times 1.95 over 9.8, square root of the whole thing, and I plug that into my calculator. Square root of 1.95, close parentheses, divided by 1.8, close parentheses. I get that my hang time is 0.6308, so I think we could probably call it 0.631 seconds. I'm going to add that to my T chart over here. Grab all this and group it and move it out of our way. So now we've got hang time. Do we even have to go back and find delta x? Not on this problem. Okay, we could at this point because we've got t. What we really need is our VF. I think big 5 number 2 is going to be perfect. So big 5 number 2, VF equals VO plus AT. I'll do it in red. All right. Since VO is 0, then we're basically just going to say final velocity equals acceleration times time. So that's going to equal 9.8 times 0.631. So I'm going to take my calculator answer, which is a 0.631. I'm going to go times 9.8. I get that my final downward velocity is 6.18 and change. So coming back over to my triangle here, so this down here is 6.18. We can use Pythagorean theorem to solve for v, for our final total velocity vector here. I guess we can call that like vt for v total, or vr for v resultant, whatever you want to label that as, just so you know that vf is different than the other vf.
Wait, so this VF is for, okay, so when we need to find that one?
Yes, okay. Because that's what the problem's asking. It wants to know what our landing velocity is. We are going to go ahead, after we find this, we're going to find what angle it is too, because velocity has to have direction. And so we're going to need an angle to show direction, not just speed. So when we do this, if we do v squared equals 6.18 squared plus 3 squared. So 6.18 squared, I'm going to go answer squared. I get 38.22 when I square that, plus, now 3 squared is 9. So 47.22. So 47.22, we need to take the square root. Square root of my answer. I get 6.87 for my final velocity vector. I'm going to write that in right here in green. Meters per second. Now we need to find an angle. I think probably the easiest way to do that is because we've got our 2 legs that have been given to us. I'm just going to use tangent. So let me resize some of this mess here, get it out of the way. Good. Thank you.
So that's the answer that it's asking for on
That,
number 8?
That's part of the answer it's asking for. It's not the whole thing. You still need to grab an angle. Okay. So I want to find, let's go for the angle. Oh, which angle do we really want to look at?
Maybe the bottom one?
I think it would be the bottom one, because we're going to want to know like what angle it makes with, well, technically you're supposed to go with the angle that is either north or south of your horizon. So this angle here would be the same as this angle down here, right? Because we got the whole, opposite interior angles are congruent. So then this is going to be opposite. This is going to be adjacent. So we're going to say for our theta down here that the tan of theta going to equal 6.18 over 3. Did it? So I'm going to hit second tangent. And I'm going to do 6.18 divided by 3. Make sure I'm in degrees and not radians. And it tells me that the angle down there is 64.11 degrees. Okay, so I'll go ahead and put in as my angle at 64.1 degrees. And we could say north horizon or from the ground level. But that is our answer. Before we move on to the next set of stuff, this is an excellent place to ask any questions you might have. Okay. And let me get you all some part 2 problems. Make more a little love looser. Bless you. Bless you again. So, what I'm going to do to start this off is I'm going to go ahead and show you a derivative from a couple of our big fives that are going to be necessary to solve this first problem. Okay. So if you look at this first problem right here, let me get the workspace pulled back up. So in 1993, Wayne Bryan threw a sphere a record distance of 201.24 meters. That's impressive. That's like, more than 2 football fields. It's not an official sport record because special device was used to elongate Bryan's hand. Suppose he threw the sphere at a 35-degree angle with respect to the horizontal. What was the initial speed of the sphere? So let's talk about what we know here. Okay, we know that Bryan is down here chucking his sphere. That's a sphere. He's got a pointing on it. Okay, and he's going to chuck this sphere, and it's going to travel a total distance of 201.24 meters. Now, we're going to make an assumption here that he is throwing it from ground level, even though he's just slightly over ground level, because they don't give us that. So the only assumption we can make is that it's going to be leaving the ground close to ground level. Now, based on what you know, what kind of flight path is this going to make? What's it going to look like? Good, everybody just did the arcing finger thing for me. So yeah, it's going to be kind of a parabolic arc. Going to sort of do that, right? Further, from some of your other studies and some of the things you've been playing with in lab, you know that at the top of the arc, right here, what is its y velocity going to be? 0. Excellent. And because you've also played around with some of this, you know that the time involved right here, the time going up, is going to be equal to the time involved right here. Agree? Yes. Okay. So basically, when you've got a problem like this, you have to split it into 2 different pieces. Okay? You're going to have the up part and you're going to have the down part. And we refer to this as like the upward half of the flight and the downward half of the flight. And if you consider these as two separate problems, then everything makes sense. But basically what that means is that everything that you've been doing for your projectile motion stuff so far, you're going to kind of have to double it. Okay? You consider up and down as two separate events. Now this one right here, the only other information we're given is that the angle of his upward flight is 35 degrees, right? Now, because of the symmetry of this whole flight, we also know that the angle it's going to be landing at is 35 degrees, coming back the other way. But what we don't know is we don't know what his starting velocity is. Now this velocity is not just a y velocity. This velocity is a resultant of both the x vector and the y vector of his throw. Because when you throw it at an angle, part of that is going this way, part of that is going this way, right? So, with what we have, we're going to have to do some heavy-duty math weirdness and wizardry to figure out all this. So I'm going to go ahead and I'm going to skip to the very end, and I'm going to give you a new formula to write down. You can't write it on your Big 5 chart because it's already laminated unless you want to get a Sharpie and do it later, and I'm fine if you do. But we like to refer to this one unofficially as Big 5 number 6. It's like the fourth movie in a trilogy sort of thing. Okay. Big 5 number 6, when you've got a situation just like this one, where you are trying to find its original upward velocity, you know the angle, and you also know the total delta x. Then you can plug those into this little baby right here, okay? VO.
Wait, you know delta x and y?
Well, we know delta x because that's how far it went, right? Okay, that's the total delta x. That's the delta x up and the delta x down. Okay, which half of that would be about 100.5 or 100.6 something, and the other half would be 100.6 something. You know the angle, and you're trying to find that original VO. Okay, so use this. VO equals great big honking square root sign of negative a delta x over 2 times the sine of theta times the cosine of theta. I may actually end up recording a whole different video just kind of explaining how that works, because we worked it out last year, and it took us like a few days to figure out how the heck we were supposed to derive it. But if you are okay just taking my word for it that this works, and that'll save us all a lot of time and pain. Okay. So, given, if we're going to go with the assumption that this does in fact work, let me shrink it down a little bit. Move it up here. Then let's take what we know and what we're given here and plug it into this thing. We know that VO, shrink all of this stuff down here. So much stuff. Yeah, that's fine. So, VO is going to equal square root of negative a delta x over 2 sine theta cosine theta. So let's see what that actually translates out to in our problem here. going to be equal to negative a times delta x. Delta x here is this 201.24.
Wait, is A still 9.8 because of gravity?
Yes, and hold that thought for just a minute, because either it's going to be positive 9.8 or it's going to be negative 9.8. Yes, I'm glad you brought that up. The A we're referring to right here is acceleration due to gravity, or G, which is 9.8. Okay? Divided by 2 times sine of 35 times cosine of 35. We're going to my calculator. Actually, that A, let's go ahead and change that to 9.8. Oh, it's going to be 35 there. Dang it. It only does that. Oh, you're all in good thing. You know what? I'm so very sneaky.
So it's still be negative.
One of two things is going to happen. Okay? Okay, now please hear me when I say this. If all of what's on the inside right here makes a negative number, then you can't square root it, right?
Mm-hmm.
And so in that case, it would be the negative of a negative, which is going to just make it a positive. But changing it back over to a positive and then square rooting it does fix things.
Hold up.
Go ahead.
So wait, why is it? Oh no.
Okay, all right. That's a good question. So check it out. During the upward part of the flight, A is equal to negative 9.8. During the second part of the flight, A is equal to positive 9.8. Why?
Because when you're going up, it's pulling down, and when you're going down, it's pulling down. But
Exactly. So if we're just considering the upward part of the flight as its own thing, then starting velocity for y is up, but starting acceleration is the opposite direction. Okay. So this negative 9.8 would actually be negative 9.8. Okay, which would just make it positive 9.8. I'm going to plug some of this stuff in here. So I'm going to simplify this a little bit. So if I do 9.8 times 201.24, it gives me 1972.152. I'm going to do 2. I'm going to do sine of 35. Sine of 35 is 0.574. Cosine of 35 is 0.819. So now I'm going to take square root of 1972.152 divided by, open parentheses, 2 times 0.574 times 0.819, and actually just leaving it in your calculator as the sine of 35 cosine of 35 is going to give you a slightly more accurate answer. Close parentheses a couple times, hit enter, and I get an answer of 45.799. Okay, perfect. Okay, so that tells me that the starting velocity of his toss is going to be 45.8-ish meters per second at 35 degrees north of the horizon.
question, is that the answer?
That is the answer.
Because we're doing the initial speed.
Yes, all they want is the initial speed of the sphere. That's a special case. Fortunately, The only time you're going to need to use big 5 number 6 is when you're given a situation exactly like this. When you know the angle it was launched, you know the distance it traveled, but you're trying to find out how fast it was going when it first left the hand or the gun or whatever. Most of the rest of these are not going to be quite as evil. Let me see if I can find one that is not quite that evil. Yeah. Number 2 is not as evil. Let's look at number 2. That's a cool name. Before I move on, does anybody have any questions? Are you done writing this? I'll stick video up later if it doesn't break. Okay. April Moon. Yeah, I wish my parents were that cool. Set a record in flight shooting, a variety of long-distance archery in 1981 in Utah. She sent an arrow a horizontal distance of 9.5 times 10 squared meters. I don't see why they don't just say 950 meters, but maybe it was a significant figure thing. I don't care. What was the speed of the arrow at the top of the flight if the arrow was launched at an angle of 45 degrees with respect to the horizontal? Actually, we might skip this one for right now because this one also looks like it might be evil. But maybe not. Maybe not. Let's see if we can get down to what we know. Okay, so let's start off with April. Okay, with her long, flowy, awesome hair. And she's got her, bow. And she's shooting her arrow. And just like before, it's going to follow parabolic flight path, right? We're going to have the apex right here, which is going to be halfway through. And we know that her total delta x was 950 meters. Okay. What they want to know is what's the speed of the arrow at the top of the flight if it was launched at 45 degrees with respect to horizontal. That's kind of actually beautiful. Because I think what we're going to be able to do is we're going to be able to just look at the first half of the flight and not worry about the second half at all. Okay. If we do that, we're just concerned with the first half of the flight. What is the delta x for the first half? Right, so 475, is that right? Okay. I did that in my head. Okay, that's it. Okay, so 475 meters. Awesome. Now we also know that at the top of the flight, the only velocity we're going to have to worry about is the x or the y. Oh, no, the y. The y is going to be 0, right? So at that point right there, the velocity of y is 0. And we know that the velocity of x is going to be the only thing we're looking for. Okay? So we don't know flight time. That's unfortunate. We do know that if we look at how this thing was launched, it was launched at 45 degrees, right? Now, what kind of triangle does this make? 45, 45, 90, right? So whatever the original big VO total was, we know that if we square that, it's going to be equal to these. And we know that the Vx is going to be equal to the VO for y, right? Boy, okay. So we know that this right here and this right here are congruent, right? They're going to be exactly the same. So how could we express that? Okay. So here's the part where it does start to get a little bit fuzzy. Okay. We're having to approach this kind of like a surgery we're going to have to do or a toilet we're going to have to fix. I'm open to suggestions on where we go from there.
Do you need time?
I don't know.
I think like you have time to find velocity, so.
Okay.
I see that. Actually, wait, do we need to find the VO? the hypotenuse?
Yeah.
We do.
Well, I don't know if we do, honestly. So, what if we were to play this backwards? Okay, we know that this side is equal to this side, right?
Yeah.
Okay, so thinking about it, opposite. Now, what we don't know is we don't know the height that this reached, right?
Yeah.
Okay. Let's put a pin in this one, and we'll come back to that. I have a feeling that this is easier than we think it is, but I can't see it right now. Okay. 3 is going to be just like 1. Second. I'm going to jump all the way down to number 7. Question?
Number 7?
Yep.
Okay.
7 I know we can tackle. Somebody beeping?
Yeah, sorry, it's
Scared kangaroo wants to clear the fence by jumping at a speed of 8.42 meters per second and an angle of 55.2 degrees with respect to the ground. If the jump lasted 1.4 seconds, how high was the fence and what was the kangaroo's horizontal displacement? Okay, we do have to find 2 things. And same kind of thing is going to follow. We're still going to have good old parabolic flight path. We're still going to be dividing it into the up half and the down half. But let's talk about some other things we know here. We know, okay, he jumped at the speed of 8.42 meters. So we get his starting VO right here, 8.42, and an angle of 55.2. So we also know this starting angle right here, 55.2 degrees. Okay. If the jump lasted 1.4 seconds, how high was the fence? What was the kangaroo's horizontal displacement? We're really only going to have to look at the first half of this. Okay? Horizontal displacement, what they're talking about right there, that's going to be delta x. And that's going to be our delta x total. Which we're going to be able to get once we find what the x component of his starting velocity is. Okay, his v of x. Okay, because if the total jump lasted 1.4 seconds, how long did the first half of the jump last? Huh? 0.7 seconds. So we can say that for just this first part right here, the time going up equals 0.7 seconds. We also know that the time going down is 0.7 seconds.
I have a question.
Yes?
Can we do
Can we do cosine to find v of x? In order to, okay, so we've got our hypotenuse, and we've got this. Yeah, absolutely we can. Okay. The cosine is adjacent over hypotenuse. So I like that. Let's go ahead and find that. So if we say that cosine of 55.2 equals dx over 8.42, then let's do 8.42 times the cosine of 55.2. And I get that the Vx going forward is 4.805. Is that what I get? Okay. So We know that Vx equals 4.805. Okay. Now, we need to know horizontal displacement. We know the whole jump lasts 1.4 seconds. This is going to be a lot easier than I thought it was going to be. So how do we find the total delta x here? Yeah. Delta x equals v times t, and we're just looking at the x component, right? Okay, which is not going to change. That's just going to be 4.805 times total time, which is 1.4. So times 1.4. I get 6.7275 and change, so we could say 6.73 meters. Okay, so if the other ones are too tough, that one was way too easy.
So that's the displacement.
That is the horizontal displacement. Okay.
Now we have to find the
Well, yeah, we do have to find the height. So we're just about out of time for right now. I'm going to pause this, and I'm going to go ahead and keep working it, or I'll keep working it later. Or we can just start from there tomorrow and get the height. I'll be sure and save all of this.